Sequential Cooperative Bayesian Inference. This is joint work with Jesse Wang and Pei Wang, who are postdocs in my lab. In computer science and cognitive sciences, traditionally considerable attention has been paid to learning about the physical world, how to accurately represent it, and how this need shapes and constrains representation and learning. Indeed, specifically on agents who alone learn about this world. But this picture is at great variance with human experience. Humans most commonly learn together, cooperatively sharing information toward the goal of learning. From birth and throughout life, others choose information for us in ways that help us, teach us, and guide us. Indeed, qualitative accounts have emerged across language, cognitive development, and cultural anthropology that invoke cooperation between knowledgeable and less knowledgeable others to explain the feats of human learning. But these are qualitative, not quantitative accounts. While we know quite a lot about the view of learning in which one learns alone, including computational models and rich mathematical formalisms, there only recently has been a growing interest in quantitative models of learning from others. And yet, there is, as of yet, no formal mathematical foundation. That is the problem that we in my lab have been seeking to address. In the former case, quantitative models build on roughly 3 centuries of work in developing probability theory and specifically Bayesian inference. Starting in the 1700s with the work of De Moivre, Bayes, and Laplace and others, the foundations of probability and reasoning with them were developed. However, it was much later that Bayesian inference was to be put on sound mathematical footing. This required several developments, including the axiomatization of probability by Kolmogorov. After this, Joseph Doobe's work on the Bernstein-von Mises theorem, which suggests that for finite dimensional models, asymptotically the posterior converges to the true parameter. This is a notion of consistency. It also provides a notion of efficiency in the asymptotic rate of convergence. Since this time, there's been a great deal of work refining these notions as well as addressing important challenges left open, including the robustness of these models to misspecification. Our goal today is to provide a similar mathematical foundation for cooperating agents, specifically given a teacher and learner where the teacher chooses a sequence of data for the learner and both know they are cooperating. Does consistency hold? What is the rate of convergence? And is the system robust to deviations? The impact of these results would be to form a foundation not simply for modeling learning, but for mathematically reasoning about what models can and cannot do. To do so, we build on cooperative inference, which is a system of 2 interrelated equations describing how learners would update their beliefs about hypotheses given data, which is going to be related to the probability of the hypotheses times the likelihood of the data given the hypothesis. And this is almost exactly Bayes' theorem with one important exception, which is that the likelihood does not simulate random sampling, but instead purposeful selection, which is described on the right-hand side. It's the selection that you would get from a knowledgeable person who is trying to help you. Here we'll call them teachers for shorthand, although no commitment to education is implied. So we want to say, what's the probability that a teacher selects data given a hypothesis? If we look at the numerator, we see that that's related to the prior probability of the data and the likelihood of the hypothesis given the data for the learner. We can see that these 2 equations are interrelated, so the teacher refers to the learner and the learner to the teacher. We can solve this by inserting in this first part the standard random sampling that you would use for any given problem to derive the learner's posterior, which we could plug in the right-hand side to derive the teacher's selection process, and so on. This would set up a fixed point iteration that provably converges, which is equivalent to Sinkhorn scaling. In doing so, we combine Bayesian belief updating with choice theory. Note that in this connection to choice theory, we will omit the softmax choice, essentially assuming that we're dealing with probabilistic data selection. but we could add it back in and derive theory for that as well. In sequential cooperative Bayesian inference, we seek to understand sequences of cooperating agents. So to set up the problem, we can think of hypotheses, which are of size m, data of size n. We'll assume a likelihood, what you might think of as a likelihood matrix, but is in fact a little bit more general. What we'll refer to as a common ground matrix M that's shared between the teacher and learner. We'll relax this later. We'll think of a teacher's matrix, which specifies how they sample data, and a learner's matrix, which specifies how they draw inferences. These are directly derivable from the M matrix separately. The teacher has a true hypothesis in mind. The learner has a prior over possible hypotheses, which lives in P of H here, which is an m-1 dimensional simplex. The teacher has a prior on the data. Iteratively, each of them can solve these problems. So the teacher can take M and derive M star through that recursive process that I described, which is also known as sinkhorn scaling, given the priors, and sample a data point given the true hypothesis, passing it to the learner. This will create a sequence of data, which the learner observes one at a time. Meanwhile, the learner can also derive from M star, based on the priors, for their to create their L matrix. They can observe the data that the teacher has selected and calculate their posterior. This will create a sequence also, and our consistency question is whether that sequence converges to the true hypothesis. The teacher will have an estimated learner posterior. For the first two results, we'll assume that the teacher knows exactly the learner's beliefs. Our first result is the proof of consistency. The posteriors, unfortunately, we can't draw upon the methods that were used to prove the consistency of Bayesian inference because those assume that the likelihood is fixed and unchanging, whereas ours changes based on the learner's beliefs. So we view the sequence of posteriors as a Markov chain on the simplex. By studying this chain, we can prove that the sequence of posteriors is consistent. That is, as a sequence of random variables, theta k converges in probability to the delta distribution centered on H. To illustrate consistency, we can simulate what happens over iterations. On the top row, you can see is SCBI, and the bottom row is standard Bayesian inference. The first graph, which is a triangle, represents the three hypotheses. At the apex is the target hypothesis that is going to be learned. In the middle graph is the probability of the true hypothesis accumulating over iterations. The right-hand one is the probability of sampling each of the three data points. As this resets, you can see that the data points start randomly distributed and then accumulate at the top. In fact, we can watch that accumulation in the middle graph, seeing that SCBI accumulates probability of the true hypothesis more quickly than standard Bayesian inference. This is for a specific case represented by the M and theta at the bottom. If we turn our attention to the right-hand side, we can see that in fact there's another example of M and theta, but illustrating similar points. That is, the points flow upwards to the apex, to the true hypothesis, and SCBI accumulates data faster, accumulates probability on the true hypothesis more quickly than Bayesian inference, a result that we can prove and quantify. In fact, we can formalize our observations about rate of convergence in a theorem. The theorem says that when we take the logarithm of the ratio between theta h, the true hypothesis, and 1 minus theta h, any other hypothesis, as a random variable, the expectation has linear growth to infinity. The slope of this linear growth is related to the minimal KL divergence between columns of a matrix related to M. We can compare this to the similar result for Bayesian inference, which also has asymptotic behavior that's related to KL divergence between columns of M, but note that this form of dependence on M is somewhat different. We can quantify or illustrate this rate of convergence by running simulations for a variety of cases. Here we'll focus on the case with a matrix of M matrix with 2 columns and varying number of rows on the horizontal axis. 2 different metrics are used. In the blue, we have the average difference between the averaged rate of convergence of SCBI and BI, and we can see as this it starts above 0, indicating SCBI is faster, and the advantage is increasing with the number of rows. In the red, what we see are the probability of SCBI having a faster rate of convergence than BI. So it's not about the size, but just whether it's larger. And we can see that by about 25 points, with probability very close to 1, SCBI is faster. This is one example. We've done simulations across a whole host of cases that show a similar general trend. Having proven consistency and derived the rate of convergence and demonstrated convergence, we now turn our attention to the case where there are perturbations on common ground between the teacher and learner. Here we'll focus on the case of the prior, theta, although we have simulations for perturbations on M as well. Please refer to the paper to find those. So what we want to know is when the teacher's knowledge of the learner is not accurate. We can prove a theorem in this case talking about the asymptotic behavior at SCBI. In particular, the sequence of posteriors is going to converge to a linear combination of hypotheses, which is going, in particular, it's not going to converge to a delta function, so we no longer have the strong consistency that we had before. Although we don't have consistency, we can ask, how regular is the drop-off? To do so, we can think about a case where in the middle of this circle is the teacher's believed prior, and each of these lines represents a direction along which the learner's prior might deviate. So if we go up this blue line, the learner's prior is closer to the true hypothesis, being the simplex we saw before. If we go down the red line, the learner's prior is further away from the correct hypothesis. And what we can see from the graph on the right is that as you move away, there's a linear drop-off in all directions. The blue direction, you do not get hurt because the teacher is pessimistic. In the red direction, it's worse because the teacher is overly optimistic. But across all cases, we have a nice linear drop-off, suggesting that there's continuity, but also that the deviations will not hurt too badly. When we began, we argued that for cases where the learner is learning alone about the world, we know quite a lot. We have strong mathematical formalisms. We have lots of computational models that build on these formalisms. However, for the case of interacting with other agents, especially cooperating agents on the right-hand side, we have a new world of computational models, but we don't have strong mathematical foundations. The goal of this work was to provide some of those mathematical foundations. The consequence of this work, of course, is that we might be able to reason about whole classes of models together. And so what we've shown is we've constructed SCBI for sequential cooperation, iterative cooperation. We've proved that it's consistent. We've derived the asymptotic rate of convergence. We've compared the sample efficiency of SCBI with Bayesian inference, showing that SCBI has strong advantages, as we would expect. And we've simulated some cases with perturbations to common ground, showing that there is a graceful drop-off, suggesting that the process is robust to deviations. All of these, I think, provide strong foundations for further computational modeling, as well as the potential for deriving new theoretical frameworks that unify qualitatively different models.